Hello, everyone. Our topic here today is attacking NPUs of multiple platforms. First, please let me introduce ourselves. We are from Baidu Security Lab X team. My name is Zhang, and I am mainly focused on binary and low-level system security. Le Wu here is a very experienced security researcher focused on Android system. He has found hundreds of security vulnerabilities of different vendors, and he will show us the Qualcomm and NPU exploitation in this talk. Here's the agenda of this talk. We will first talk about some basic concept of neural network and NPU, and then we will detailed focus on Samsung Exynos, Apple Silicon, and Qualcomm Snapdragon MPU, including their implementations, bugs, and exploitation. Okay, so what's NPU and why we need it? Well, before we dive deeper, let me introduce a bit about neural network. To simplify, it is a data processing process with multiple algorithm layers. It can find patterns from the raw input data, like image or sound data, and generate a result, such as image classification or recognition. It has been used in lots of areas, such as Face ID or self-driving car. The convolution neural network, aka CNN, is the most used neural network, especially in the image processing area. To understand it, let's first think about what an image looks like in computer's view. For instance, is this image of letter X? Human can find its X immediately, but in computer's view, it's just all numbers, pixels with RGB value. So how can we teach computer learn the image? And things may be more complex in the real situation. For example, if the image spins a little, in computer's view, these two images are totally different. And to solve the problem, CNN emerged. First, let's think, when humans look at the cat picture, for example, our human brain will recognize there's a cat's face, cat paw, and cat's tail. And our brain combines all these features, and we know it's a cat. CNN's idea is pretty similar. It uses a specific image pattern called filters to do the feature detection. For example, here the filter represents the upper left part of the letter X, and we can multiply each element of the filter by the corresponding element of the image region, and sum up these products. And we will get a weight result, which represents the similarity between the filter and the image region. And the blue field, as we can see, the weight is calculated is only 1, so it's less similar with the filter. With this idea, we can continue slide the filter and calculate every weight result for each input image regions, just like our human eye scans through a cat picture trying to find which part is most likely to be the cat's face. And we will get an output feature map. This information will be used for the final processing. And this operation in CNN is called convolution. In fact, there will be multiple filters to represent different features. And finally, we will get a multiple output feature map, which will be the input data for the next layer. In the real CNN operation, besides convolution, there are some other algorithms, such as activation or pooling. We will not discuss more about these algorithms here. Just remind they all do lots of parallelized computation for the feature learning. And to do the prediction, a neural network needs to be trained first. Simply put, the training process is like a loop to change parameters of every equations in CNN and find the most suitable parameters that fit the data set best. The final output of training is a model file. We can use this model file to do prediction or inference. So as we can see, convolution needs hardware to handle the massive computation, and this computation can be parallelized. So CPU is not good at parallel computing because of the limitations of the core numbers. GPU is a multiple choice, but it is very power consuming and not designed specifically for the machine learning. So we need new processors to meet the requirements. In the AI processor area, besides GPU or FPGA, ASIC chip is the most used solution, such as Intel's VPU, Google's TPU. They may have different names because their hardware implementation is different, but in this talk, I will use NPU, the neuron processor unit, to identify all these ASIC chipsets. Here is a brief architecture for the Qualcomm NPU. It's a very typical NPU design. The blue fields are SRAMs. They mainly for saving the input, output, and weight data. They all communicate with main RAM through DMA. And it has one control processor and 3 NPUs for doing the parallelized computation. It also has a unique instruction set called 电脑语. It's SIMD, so one instruction can complete the processing of a group of neurons. There is also a kind of NPU for edge devices. These chips only do inference, not for training. So it needs pre-trained model file, and they always have lower power consumption considered they're on the mobile devices. We will mainly focus on this chip in this talk. So as we said, to do the prediction, we need pre-trained model file, and the vendors always have their own model file format, such as Samsung NSYS model file or Qualcomm's DLC model file. They're all vendor designed, so there may be some file parsing issues in their runtime library. And the MPU driver and the MPU firmware are also big attack surface. Okay, now let's take a look at Samsung Exynos MPU. Here is an overview of Exynos 9820. It has one control processor and 2 MPU cores for doing the parallel computation. The input feature map first will be divided into multiple parts and delivered to the MAC array layer. The MAC here means multiply accumulate. This dual MAC unit will finish the multiply and adding computation. The control processor here is a 32-bit ARM v7 processor running a RTOS system by Samsung, which has a complete subsystem design, and we'll talk more about it later. The testing device here is Samsung Galaxy A54 and A51. MPU devices node is Vertex 10 in device folder. The device is accessible from Untrusted app according to its SE Linux policy, so we can open and send IO control within the app context. For Galaxy phones, these operations are all wrapped by EN framework, such as camera service using this framework libraries to talk to the MPU driver. From kernel's view, MPU device is a typical platform device. In device probing stage, system will allocate few DMA space for initializing. DMA is direct memory access, which means the DMA controller hardware will transfer data between the kernel and RAM, between the device and the RAM directly without using CPU. And after allocate the DMA space in RAM, its physical address will be saved in schedule list structure for later configure the IO MMU page table. IO MMU is the hardware for translating the virtual address of IO device to the main RAM's physical device. And IO device virtual address is called IOVA. When a DMA request happens, the IO MMU hardware will automatically finish the address translation based on the page table that we create here. IOVA value is gotten from device tree source file, aka DTS. It saves the IOVA size and name of different IO mem space. And the whole address mapping is like following. The red line area is for non-DMA space, which are mainly devices IO map space for controlling the hardware. Kernel will map this IO map space to virtual address for later use during the probing stage. The last three space is for DMA buffer. They are mainly responsible for communications between kernel and NPU. Besides, the device also has other DMA space which for dynamically allocation. The related address information is also saved in DTS file. Okay, the previous process we talked about are all finished during the Android system booting period. Now let's take a look at the device opening process. When user open the Vertex 10 device, kernel will first load MPU firmware image to the DMA buffer. The firmware image is located in 3 possible locations or dumped from Android boot image. Kernel will try to load firmware from either one of these paths. And the image is now encrypted or signatured, so we are able to run our modified program on the MPU core, such as hook functions or print debug message. And after loading the MPU firmware, kernel will power on the MPU control processor, and the MPU will begin execute the firmware RTOS. Another thing kernel will do is to start a kernel task to handle the data transfer between kernel and MPU. The work task will enqueue all the MPU requests and serialize them on the ring buffer. Okay, now let's have a brief summary. Well, device probing stage, system will allocate DMA buffer, finish IO MMU configuration, and create the address mapping. When device open, the system will load firmware to the DMA buffer first, and power on the NPU control processor, and the kernel side will start a worker task to handle the data transfer between kernel and NPU. The data transfer is mainly through the DMA, so what data is on the DMA buffer actually? In fact, after loading the firmware image to the DMA buffer, kernel will set up a mailbox structure. The mailbox contains two parts, mailbox header and the ring buffer. Mailbox header mainly contains a read-write pointer points to the ring buffer, which represents the current location of the data to be parsed. There are 4 ring buffers for handling the different requests, and they all have different lengths. Kernel will first set their read and write pointers to 0. Later, when the host wants to send a request, the write pointer will be updated. And the NPU firmware will know that there is a new request from kernel by reading that write pointer. Later, when NPU finish request handling, firmware side will update the read pointer and notify kernel the request is already finished. When user space sends the NPU request to write control, the driver will generate a request structure and put it into a global request management list, which is for in-queue all the requests from different tasks. The kernel worker task, which we talked about earlier, will serialize them on the ring buffer. A request on ring buffer will be converted to structure message and structure command. Structure message represents a major functionality of this NPU request, such as command load or command process. And the structure command contains the request man payload, IOVA, for firmware to parse. Later, kernel will copy these message and command structures to the ring buffer and update the read-write pointer on the mailbox header. At this point, a sending request action is done. Again, note that these data are all on DMA shared buffer, so they are both visible by kernel and the NPU. The request data format is like following. Note that the data space is allocated through ION or DMA buff heaps. So it's not on the ring buffer or the default DMA spaces. When the request is command load, the request payload is always began with a structure called NCP header. The NCP header stores the pointer to the memory vector and address vector array. Memory vector contains some basic attributes of feature map, such as its type, its weight, or height. And it also saves an index value points to the related address vector. Address vector contains an IOVE address point to the feature map's data frame. If it's command process request, the command payload will start directly with address vector array. And its MADDR field saves the ION buffer's IOVA, which stores the feature map's data frame. Okay, to sum up, kernel and the NPU transfer data through the mailbox on the DMA buffer. A kernel worker task will in-queue all the MCP requests and serialize them on the mailbox ring buffer. Then update the read or write pointer to notify the other side there's a new request or response. The real request payload is on DMA buffer created by ION. It is a shared buffer, both between by user space, kernel, and firmware. Now let's have a brief overview of the firmware side. Like we said earlier, the firmware image is saved in the Android file system and will be loaded to the DMA shared buffer while opening NPU device. The processor is a 32-bit ARM v7 core and the RTOS system running on it, so with no modern OS mitigation. When firmware boot up, it will first need some subsystems, such as heap events. Then it will start few native tasks to handle the requests from the mailbox. For example, the task mailbox low priority function, mainly for handling the data on this first H2F, which means host to frame, for firmware ring buffer array. And this function will loop to check the write pointer on the mailbox header. Once the write pointer has been updated, the firmware knows that there's a new request from the kernel side. Later, it will call different handler according to the command field of the structure message. Oh, sorry. And after processing the request payload, firmware will update the read pointer in the mailbox header and to tell kernel that it has finished the handle request. And this is a whole cycle of request processing. Now let's look at some known issues of Exynos NPU. This vulnerability is in the world exploited. With calling two different L control of NPU, the queues format can be freed twice, and this is a very stable double free, so no racing needed. So it's very exploitable. The patch is to just set the pointer to null to avoid this double free. This CVE is a time of check, time of use bug in the NPU driver. Like we said earlier, the ION buffer is created in user space to store the request payload, and this buffer is shared by both user space kernel and the NPU firmware. When kernel malloc the heap space first time, the size is get from the shared buffer first, and the range has been checked correctly. But the kernel will get the address vector index again from the DMA buffer, causing the double fetch. To trigger the bug, we can create a thread to change this value to a very big number, and it will cause a heap out-of-bound write issue later. The patch is to get the index from DMA buffer only one time, and add more range check to prevent the out-of-bound. And this SVE is in NPU firmware. This function parser init is mainly for parsing the NCP header and the related memory vector and the address vector array. But all these inner fields, such as memory vector offset or address vector offset, doesn't have any run check. So it will cause multiple out-of-bound access issues. The patch is to add multiple run check to prevent the out-of-bound access. Now kernel side and the firmware side both have run check. But there's a problem with this patch. Let's compare the run check code from the kernel and firmware. The firmware only makes sure that offset add count plus size of should be in the correct range, but it doesn't check the address vector index. The kernel driver does. The address vector index is the index for finding the address vector. And we know that this is on DMA buffer shared by user space, kernel, and firmware. So we get a time of check and time of use bug. The check of address vector index happens in driver side, but the use is in the firmware, which lack the range check. To trigger the bug, we can start a thread in user space, change this address vector index to a much bigger value. The race window is after kernel driver's check, but before firmware's use. And finally, this time of check, time of use bug will cause out-of-bound access issue in firmware and crash the phone. So how can we exploit it? As we can see, a few lines after the bug, the local variable 14 and 15 are all user controllable, which is calculated by the width, height, and the stride, saving the memory vector, which all we control. So here we get an arbitrary address write primitive. To use this arbitrary write, we can change the native task handler to our shellcode's address. Task handler array is saved on firmware's heap area. To know what the address is, we can modify firmware to hook the malloc function, like the picture shows, because there's no integrity protection for the firmware image yet. And it will print the malloc result in the message. We can put our shellcode on the NPU heap space, since all heaps are mapped executable. Also, all shellcodes are hard-coded because there is no ASLR on the firmware, so we don't need any info leak. The shellcode I use is just a print hello from NPU string in the kernel debug message. And here's the exploit demo. The device is the Galaxy A51. The ADB shell here is demessage and grab to wait the shellcode string. As the SC-lineage policy we talked about earlier, this exploit can be finished with a normal app. So here's the string already showed. And finally, we run our shellcode in the NPU processor. As I reverse more, there's more bugs with the same bug pattern. This bug is Galaxy A54's firmware. Also, in the parser init function, the body offset will be got from DMA buffer twice, so it's also a time of check, time of use issue. Since I only audit few functions, I think there should be more bugs to be found with this bug pattern. Okay, now let's take a look at the Apple Neural Engine, aka ANE. There's some excellent work before, such as attacking Apple's Neural Engine by Simo36 and Apple Neural Engine internal by Vishu. I strongly recommend you read this if you want to look into this area. To simplify the ANE architecture, the pre-trained model file will be converted to a HWX macro format model file by CoreML framework. Then the privilege process and ANED use this file to create a ANE program. Later, app side can send requests to an NPU with this program handle. This section I'll mainly talk about some new issues of the ANE before, and the bugs I found by the patch analysis. This CVE is an ANE kernel extension. Function file index to wait doesn't check the index range, which may cause out-of-bound access. The argument index and the offsets are read directly from multiple sections of the model file, which is user controllable. The patch here is adding run check for the index. This bug is an integer overflow in ANE kernel extension. The argument A2 and the A4 are all user controllable. The integer overflow issue will cause a calculate result, which klock here, to a very small number. Later, the if check here only check whether the klock is smaller than the max range, but then check with the smallest range. So here is a almost arbitrary address write vulnerability to any address prior than the MUTK section. And this bug is a little similar with the previous Samsung bug. The kernel driver gets OP count twice from the shared buffer. So with some racing, we can trigger this double fetch and causing a out-of-bound issue. The patch is also similar to Samsung, which get the value from the shared buffer only one time. This out-of-bound write bug is in program send request function. The root cause is that the function even doesn't check the total intermediate buffers count, which is user controllable, and it will lead to out-of-bound write issue later. I found this bug with the patch analysis. The structure has changed to a new format, which input and output share the same array, which total max should be 255 surface ID, but the range check even doesn't change, so the total input buffer and total output buffer add up may be bigger than 255. So here is an out-of-bound access issue, which may cause type confusion later. So as we can see, there are lots of bugs in the parsing logic of the multiple section of the model file. In fact, I was going to talk about more bugs I found by the patch analysis, but other bugs are still not fixed yet, so I can't talk more about them. Okay, now please welcome my colleague Luo Wu to talk about the Snapdragon MPU bug and its exploitation. Thank you.
Hello, everyone. So let's start getting to the Qualcomm Snapdragon MPU driver. By opening the file dv/ms_MPU, we can interact with the MPU driver. And the MPU driver provides many I/O control commands for user space apps to use. Untrusted apps can also access these I/O control commands on some devices. Here, we will focus on two I/O control commands, which are MPU load network v2 and MPU unload network. The MPU load network v2 is used to load a neural network model onto the MPU, and MPU unload network is used to unload a neural network model. Both of them use MPU network command object to interact with the MPU firmware. First of all, let's have a look at how the command MPU load network v2 works. At first, it will allocate a MPU network object, and then it will allocate a MPU network command object by calling the function MPU alloc network command. The MPU network command object is called load command, and we can say it's allocated from a dedicated KMAP cache. After that, the load command will be queued into the command list of the MPU network. And the function MPU send network command will be called to send the load command to MPU firmware for executing. After that, the driver will wait for the load command to be completed. When the MPU firmware completes the load command, it will wake up the driver side. Since the load command has been completed, it will be dequeued from the command list of the MPU network object by calling the function MPU dequeue network command. After the dequeue operation, the load command will be released by keymap catch free. And if the stateBuf field of it is valid, the stateBuf will also be released by keymap catch free. After all these steps, the command MPU load network v2 is completed. And so let's have a look at how the command MPU unload network works. Actually, the workflow of it is almost the same as the command MPU load network v2. First, it will find the MPU network object indexed by the network handle passed from user space. And then MPU network command object called unload command is allocated. This unload command object is also queued into the command list of current MPU network object. After that, a driver will send unload command to MPU firmware and wait for completion of it. When MPU firmware completes the unload command, it will wake up the driver side. So now the unload command has been completed. It will dequeue from the command list of the MPU network. And after the dequeue operation, the unload command will be released. In addition to the releasing of unload command object, there is another important operation for MPU unload network, which is a free network. In the free network, all the MPU network command objects in the command list will be dequeued and released. We need to note this because it's the key point for us to understand the vulnerability later. Now let's talk about the bugs we found recently. Here is a question we need to think about. If we try to unload a network concurrently, what would happen? First, let's see how to unload a network in a single task. Actually, this is just the workflow of the command MPU unload network. As we can see, task A will acquire the mutex lock and allocate the unload command 1 and queue it into command list of the network. And then it will drop the mutex lock and wait for completion of the unload command 1. When it's done, it will acquire the mutex lock again to dequeue and release the unload command 1. And it will call a free network to release all the network command objects in the command list. But if there is a task B which is trying to load the same network at the same time, something strange will happen. As you can see, if task B acquires the mutex lock right after task A drops it, it will trigger the function free network here. As we have mentioned, the free network will release all network command in the command list. So the unload command 1 object will get released here. After this, when task A tries to use the unload command 1, it will trigger the UEF or double free issue. So this is the root cause of the bug. And with this bug, we can get at least 3 different primitives, including the list delete primitive, arbitrary free primitive, and double free primitive. Actually, the arbitrary free primitive attracts us most, and we start to think about how to exploit with it. Besides the powerful primitives, the bug also provides a large enough time window for us to perform the attack. However, there are some limitations when exploiting. First, MPU network command object is allocated from a dedicated keymap cache. So we need to think about how to occupy the released MPU network command object at beginning. Our first attempt was to occupy it with the MPU network command object itself. But sadly, we didn't find any exploitable routines. So we decided to perform a cross-catch attack. Unfortunately, we found it's hard to discard the network command catch slab by manipulating the MPU network command objects, because every MPU network command object gets allocated and then released immediately. Well, lucky for us, because of the slab merging, MPU network command object is sharing the same keymap cache with other kernel objects. We can manage to finish the slab discard by manipulating other kernel objects. What's more, the size of MPU network command object is 104 bytes, which is misaligned. So if we try to occupy the released MPU network command object with some common struct objects, there is a really big chance that illegal memory access would happen when these three primitives get executed. But if we try to occupy the released MPU network command object with arrays, things become simple. As you can see here, no matter where the released MPU network command object locates in the array slab, the content in the released MPU network command object can always be the same. We tried some array objects. It turned out that the file array is a really perfect victim. First of all, corrupting the first 16 bytes of file object has no side effect, which is really important because the list delete operation would corrupt the first 16 bytes of the file object. And every element of file array can be set to a valid file pointer or 0 individually, which is really convenient. And what's more, corrupting any element in file array won't cause panic right away unless you access a corresponding file object. It would be like this if we managed to occupy the released MPU network command with the file array. As you can see here, if we set the statebar field of an MPU network command object to a file object pointer, we will get a file UEF issue here. Yes, that's correct. File UEF is a very popular kind of vulnerability in recent years, and so many researchers has disclosed and exploited such vulnerabilities. Actually, me and Zhang had also come up with a new method to exploit file UEF in this year. The method is called dirty page table. I wrote a really detailed blogs about how we use dirty page table to exploit heap-based vulnerabilities, including the file UEF. And this time, let's use dirty page table directly to exploit this file UEF bug. Here I only explain some key ideas of how dirty page table exploits the file UEF. First, it would be like this if we occupy the victim file object with user page tables. As you can see, the f count of victim file object is collided with the victim PTE. Second, we can perform the increment primitive of file UEF by calling the syscall dup. By calling syscall dup page size times, we can manage to add OX1000 to the victim PTE. This can be powerful because we can manage to read or write another physical page which is inaccessible before through the user virtual address. So what if the physical page happens to be the one which pipe buffer lies in? Yes, we just controlled the pipe buffer. By manipulating the content of the pipe buffer, we can get arbitrary address read-writing easily. Here is a demo of routing the Samsung S20 device with the bug. Because of the sensing knocks, I'm using the AVC overwriting technique to bypass the SLinux and using the user mode helper technique to spawn a reverse root shell. Okay, that's a demo.
Okay, the conclusion, I think there are still many time of check and or double fetch bugs in the MPU device to be found. And the patch analysis is a very useful way to find new bugs. And I think Android vendors should correctly enhance the SLinux policy to restrict resource access. For the future work, I think firmware side can be reversed more since they are really lack of review. And the model file parsing and the lower level hardware implementation may also be a big attack surface. Here are some resources that we refer. If you're interested in this area, I strongly recommend you read them. And that's all for the talk. Thank you very much.